Okay, so when you look at this problem, one of the things you have to remember, this notation. So that is a composition notation. Remember that that means f of g of x. That really looks like a crayon, doesn't it? Anyway, so if you do that, first you want to find out what g of x is. So we're going to use our g function, and we're going to plug in the -3 there. Now, when you do that, we're going to get the square root of 9 minus, in parentheses, -3 squared, which is going to become the square root of 9 minus 9, or the square root of 0, which is 0. But then when you go to plug that into the f function, 1 over 0 is undefined. So the answer would be D. Yeah, be careful with that. That is a very common thing that is done. So just anytime I'm inserting a value into an expression or function, I tend to surround the whole thing in parentheses so that I don't make that mistake. So that's a good rule of thumb. Okay. So the answer was undefined. Remember, 0 denominators are undefined, 0 numerators, just 0. Okay. So in this lesson, we are just going to remind you of some rules of functions. This is not going to be anything really new. You will notice that we will have some functions that aren't necessarily defined as anything more than a graph, which is a little unusual. Usually we're going to give you that algebraic equation that matches it. So it's a little more abstract thinking than in pre-calc last year, okay? But it's going to be very similar. So some definitions that we need to talk about. Remember, a function is just a rule that assigns each x in a set D, the domain, exactly one f of x in a set R, the range. A function is a rule that assigns each x in a set D, the domain, exactly one f of x in a set R, the range. For most purposes, and for our purposes as well, the independent variable is our domain value, or our x. The dependent variable depends upon which x we choose. That's a good way to remember it. And it is the range value, y, or f of x. So remember, you can think of a function like a machine. I have an x. It goes into the function. It comes out the other side as an f of x. So you want to think of a function like a machine. It is an input-output device. I am inputting something. I am getting a value because the function did something to it. Maybe the function adds 2 to it. Maybe the function triples it. Maybe the function squares it. Maybe the function does lots of different things to it. But you want to make sure that you think of a function like a machine. Input, output. I input something. The function does something to it. It comes and flips to an output. Remember, ordered pairs can be thought of as xy or xf of x. You decide how you want to think about it, but you should be able to transfer back and forth in that notation. So you should be able to transfer back and forth between notations. And graphically is probably the easiest way to tell something is a function or not, because you can use the vertical line test. Because that is 1x is assigned to exactly one f of x, the vertical line will detect any that are paired up incorrectly. So the vertical line test is very helpful. So if any vertical line passes through the graph of an equation and hits it in more than one spot, then it is not a function. So if you have the graph of something, that's the easiest way to tell if it's a function or not. If you can explicitly solve the function for y, and then you don't have any like pluses or minuses, like a plus or minus square root is not going to be a function. But if you have a vertical line test, that's the most precise way to tell whether or not something is a function from the graph. So those are all things you probably remember from last year. Those shouldn't be anything different than what that we've done in the past. Again, you may not have necessarily a precise function. Sometimes they even just give you certain points. Oh, f of x is 2, or f of 3 is 2, and f of 4 is 7, and what is this? So sometimes they're even vague about what the function is as a whole. But those are the main things to remember. That x is your independent variable. It's assigned to exactly one y, or f of x for functions. Think of a function like a machine. If you want to look at the graph, a vertical line test is going to tell you if it's a function or not. There are 4 main ways to represent a function: verbally, numerically, visually, or graphically. I think that's the way you spell graphically. Is it 1 L or 2? Anyway, and algebraically. Okay, so we will kind of get into a habit of doing multiple ways in which we can represent a function, depending on what we're trying to accomplish. But it's helpful to know that the algebra should represent what the graph is saying, should represent if there's words, what the words are saying, and the numbers should all match up. So all those things should go together, or one of them is wrong. So I always tell, calculus students, if you're doing a problem and you are doing the algebra and you're unsure if the algebra is right, why not use a graph to check your work? Find Desmos, put it in Desmos. Does it support what my algebra has said? Okay, so that's a really good way to check your work. They should support one another. If not, one of them is wrong. So we have to remember about function domains and ranges. Domains, remember, are the x's. You're asking yourself what x's work. 3 ones to have memorized. Fractions, the domain will always exclude where the denominator is equal to 0. So remember, fractions, everything is going to work except where the denominator equals 0. So throw out any values where that happens. For square roots, the input must be greater than or equal to 0. So sometimes you have to put the input, the square root, under the square root thing, greater than or equal to 0, and solve that. Polynomials are so wonderful because all real numbers are going to work. You can even put in that category sines and cosines. The hardest thing to determine about a function, I think, are the ranges. And you pretty much have to look at the graph in order to find the ranges. We don't have a really great way to find the ranges otherwise. I mean, you can sometimes do the inverse of a function and then kind of look at that, and that sometimes will help you, but that's a lot of work. So knowing what the graph of something looks like is very helpful in finding your range values. But I very rarely am going to ask you to tell me what a range is, unless either it's something I know you know how to graph, or I know it's something that I'm going to provide a graph. Other than that, most of the time we're going to be focusing on finding domains, because you should algebraically be able to find a domain. And I'll show you examples, when we need to. Speaking of one, here's a function. So we've got this function f. It says, looking at the graph given, find f of 1 and f of 5, and what are the domain and range of f. So let's start with f of 1 and f of 5. Now, let's assume, if I was able to, which it was hard to do on the application I was using, let's assume these are perfect integer points. So if you want to make those line up perfectly, let's assume those do hit at those nice values, okay? So that's one thing. Assume my points are filled in, there's no arrows, it stops at those nice pretty points, okay? So first thing it says was to find f of 1. Now remember, in f of 1, our x value is 1. So you're just going to find where the x value is 1, and that is the point 1, -3. So the value of f of 1 is -3. Please don't make these harder than they are, okay? F of 5, we go over to where we have an x value of 5. And let's assume it hits at that nice point 1. And so f of 5 would be equal to 1. So be very careful about, don't overthink it. F of 5 is saying, what is the y value when our x value is 5? F of 1 is saying, what is the y value when our x is equal to 1? So again, don't make those more difficult than they have to be. Are we good with A? Okay, now let's take a look at B. Back in pre-calc, we talked about domain and range, so this shouldn't be something new. The domain are the x values that we cross or use from left to right. And so please get in the habit of using interval notation for me. Let's assume that point is colored in. We use a value of -7. There's no values we have skipped. There's no discontinuities or anything funky. And we use all the way up to +7. So remember, we denote the fact we use those things with a bracket. If there was an open circle somewhere, we would have to skip it and we would use a parenthesis, okay? The range, remember, think of the y values as the lowest to the highest. So the lowest value to the highest is what you want to think of. Our lowest value is -3, and we have a point there. Our highest value is +3, and we also have points and every point in between. So you're not going to be given a range or asked about a range unless you have a graph to go with it most of the time, because again, range is something that is just a little weirder unless you have a graph. Everybody good with that one? Do we have any questions? Okay. For this example, it's just trying to remind you how things graph. Now it says sketch the graph and find the domain and range of each. I would sketch the graph first and then answer the questions, but we will also talk about how you can just look at the function and know some things. A is a linear function, y equals 2x minus 3. Hopefully there's no question in your mind how to graph that. Go to the y-intercept of -3, go up to over 1, up to over 1. Also with linear functions, you can plot points. You can plug in 1 and get a value of -1. Plug in 2 and get a value of 1, and so on. So linear functions, graphing those should not cause you any grief, I don't think. So it is a type of polynomial. So without even graphing it, I hope that you know that the range is from negative infinity to positive infinity. We do not put brackets on infinity. We're never going to reach those values. So always put a parenthesis on a infinity or negative infinity. What shape do we have in B? It's a parabola. What does the plus 1, because of our rules of transformations, do to that parabola? It lifts it up 1. So normally our parabola good points are 0, 0, 1, 1, negative 1, 1, 2, 4, and so on. But all those points just get lifted up. The vertex is at 0, 1. And then we lift those points. If you forgot that, so there might be contexts where it would say give your answer in interval notation, but for me, if you use the all real symbol, like for the domain for this one, you can do that. I didn't do the range for that, and we'll come back to that. But the domain for this one, since it's also a polynomial, you can write the infinities or you can write the real number. That's okay with me. Yes, that's fine. Now, the range for the left one is what y values occur up and down. And so you'll notice we can go down as far as we want. We can go up as high as we want. We don't skip any. So the range for this problem is the same, all real numbers. Okay. But for a parabola, because there is a low point and a high point, you do have to, be careful about the range for this one. The lowest point is positive 1. I do have a value that I can stand on at positive 1. And then I can go up forever and ever and ever and ever. So make sure it was a bracket. It was just a very sloppy bracket. But please make sure that for all real numbers, you do the double back. And for range, you just do a plain old R. So please make that notation that I can clearly see that it means the all real numbers, okay? Everybody okay with example 2A and B? Okay. Here's just some practicing using function stuff. We're going to just do the first 3 on this page. There's not enough room to do the last one. So let's do the first 3. And let's start out with f of negative a. Like we saw in the opening, little 5-minute check question, if you don't use parentheses, it can throw you off a little bit. So when I input this negative a, wherever I see an x, I'm going to put a parenthesis containing negative a. That will allow me to not mess up my order of operations as often. So I would tend to use that notation. So this would be a positive a squared but times 3. This would be a negative 5 times a negative 8, or a positive 5a, and then plus 2. So watch out if you use, if you're inputting anything, use a parenthesis as a guide for you, okay? Yeah, you can. And then now we're going to plug in x plus 1. Again, I will use that notation. Let's go ahead and plug in x plus 1. So we have 3 times the quantity of x plus 1 squared minus 5 times the quantity of x plus 1 plus 2. So use a parenthesis to help you, okay? So here's the key to this particular problem. Make sure you think of x plus 1 squared as x plus 1 times x plus 1. And you can even expand it even right here. Or sometimes I'll expand it to the side so that I can do that math and then substitute it back in. X plus 1 squared, if you were to FOIL it, distribute it, whatever you want to call it, it's x squared plus 2x plus 1 as a most simplified version. And so then let's take our 3 and distribute in that in, and then let's distribute our negative 5 in. So we get 3x squared plus 6x plus 3 minus 5x minus 5 plus 2. And then just go down your list. Do we have any like terms? We do. We have the 6x and the negative 5x is an x. And then we have a positive 3, a negative 5, and a positive 2, which is 0. So that's as far as we go. Everybody good with that one? Okay. And then we have an f of a squared. You good? Okay. Okay, so here, what I would suggest doing, if we follow order of operations, the first thing we have to do is plug a into our function. And that's pretty nice to do, if I would actually do it. We take out the x, and we replace all of those x's with a. So that's kind of like that first step. Now, there's a square there, so you want to make sure that you multiply it out. So I would definitely use 2 of them to make it so that it's nicer for you when you go to distribute. So first let's distribute the 3a squared. We get 9a to the 4th minus 15a cubed plus, not that, 3a to the 3rd. So I've just distributed the 3a squared everywhere. And now I'm going to distribute the negative 5a, and it's negative 15a cubed plus 25a squared minus 10a. And then finally, I am going to distribute the 2. Now I will tell you, the algebra in a calculus class itself is not super, super difficult, but it's very easy to make stupid mistakes because it might have like this, those long, long expressions. Okay, now I'm going to distribute the 2. I'm going to get 6a squared minus 10a plus 4. Okay, so our highest power is the a to the 4th. There's nothing else, so it is what it is. So then if we look at the cubed, and I think I did one of them wrong, didn't I? Okay, wait, let's see. So that went to that and that and that. This one's wrong. Okay, sorry about that. So what is that? That would be 6a squared. Let me just go down the list. As I was saying, it's very easy to make silly mistakes. Okay, so the next thing we're checking for are the cubes. There's a cube here and here. That's a total of negative 30, a cubed. And then we have a few a squares. We have 6 plus 25 plus 6 is 37a squared. And then as far as the a's go, we have a negative 10 and a negative 10, or negative 20a. And then the 4 is just hanging out. Okay. So that would be our final answer, as long as I didn't make any weird mistakes. So that is the function f of a, the entire thing squared. So just be careful of your algebra. As you can see, it is very easy to make some little mistakes, okay? And then let's finish this off with the thing we see in the back there. I'm going to write it a little nicer for you. That is f of a plus h minus f of a all over h. Now, in this course, that is going to be something that we explore when we start to learn about derivatives. That is called the difference quotient. Now, the difference quotient is really nice because if we do the difference quotient to most types of expressions, it should reduce down for us really nicely and get something much nicer than you expect. So if it doesn't reduce down, it kind of tells you you've made a mistake somewhere. Okay, so I'm going to do to the side f of a plus h, and I will definitely need more room than that, so let me scooch that over. So f of a plus h is 3 times a plus h squared minus 5 times a plus h plus 2. Okay. Now, a plus h, when we square it, if you want to write to the side a plus h times a plus h, you can. When you square that, you get a squared plus 2ah plus h squared. And then let's distribute the 3 and the negative 5 to the a plus h quantities. So we get 3a squared plus 6ah plus 3h squared minus 5a minus 5h plus 2. Now, sometimes in this, at this point, there will be some like terms. Very often, there is not. And this is a particular one where everything is different. You can't combine anything. Stop, you're good, okay? Now, the next part of our expression, so I've done f of a plus h. The next part of our expression I need to do is f of a. So I'm going to do here, and I'm just going to write out f of a. F of a is 3a squared minus 5a plus 2. You're just replacing the x with an a. You've inputted an a instead of an x, so it's a very simple replacement. There's not much you have to think about. Now that we have those quantities, let's place them into the formulas, okay? At this spot, we have to write f of a plus h. So f of a plus h, we've done that. It is 3a squared plus 6ah plus 3h squared minus 5a minus 5h plus 2. But we are subtracting our f of a value. So put it in parentheses, 3a squared minus 5a plus 2. And we are going to take that all over h. Okay, so let's look what I've done again. This is f of a plus h. Then we put your minus symbol in parentheses. Now we're going to put our f of a. Okay. Now, mathematically speaking, the next thing we can do is distribute that negative to all those things. Okay. So now I've got 3a squared plus 6ah plus 3h squared minus 5a minus 5h plus 2 minus 3a squared plus 5a minus 2 all over h. Now, here's what should happen at this phase. Once you have all the terms listed, everything that does not contain an h should have an opposite and disappear from the problem. Okay, so what do I mean by that? Well, if you look, 3a squared does not have an h. There's a negative 3a squared to cancel it out. Negative 5a doesn't have an h, but there's a negative 5a and a positive 5a. They're going to cancel out. Positive 2 doesn't have an h, but there's a negative 2 to cancel it out. And sometimes some of the other pieces will cancel. In this case, it didn't. But let's write the pieces that are left. all of the pieces that didn't cancel out should contain an h and be divisible by h. To divide by a monomial, you don't just cross it out once. It is divisible into all of the terms in the top. So we're going to divide it out of everything. If we divide everything through by h, we have an answer of 6a plus 3h minus 5. Okay, so those difference quotients, that should always happen, or you've not done it right. I mean, so that's just a way to check. I always know if I get to this point and I have something that isn't divisible by h, somewhere I made a stupid little mistake somewhere along the line. And you can see how easy it is to do that. Just because of the nature of what you're doing, it's easy to make one little mistake along the way, one sign difference, and you're screwed. Excuse me, but it's easy to make mistakes. Okay, and if any questions about example 3? Okay, some things to remind you about lines. The formula we're going to use most often in this course related to lines, really two of them. Make sure you know your slope equation, y2 minus y1 over x2 minus x1. And then also make sure you know your point slope equation, which is y minus y1 equals m times x minus x1. So this is your slope equation. This is your point slope equation of a line. So we will use those again and again. So when they say to find the expression describing the line segment between points 5, 2, and 3, negative 4, first let's describe the entire line, and then I'll show you how to describe the line segment, okay? So if we describe the entire line, first we need the slope. So, you can label these points. Let's go in order for our x's. Let's make this x1, y1. And let's make this x2, y2. And our slope would be 2 minus negative 4, y2 minus y1, over 5 minus 3. And a really good check that you're not messing things up. This should be y's, this should be x's. This should be a pair, that's the pair 5, 2. This should be a pair, that's the point 3, negative 4. So that's kind of a way to just quickly check that you didn't mess up how you order things in the slope equation. The top would become 2 plus 4 or 6. The bottom would be 5 minus 3 or 2 for a slope of 3. And then you're going to use this to find the equation of the whole line, not the line segment. This will give us the entire line. So I'm just going to use the points 5, 2, so then I don't have any signs to deal with. So it's going to be y minus 2 equals 3 times x minus 5. Let's get that in slope-intercept form. So that just tells us to solve for the y. So we get y minus 2 equals 3x minus 15, or y equals 3x minus 13. Now, if the instruction said, find the equation of the line between the points, we would be done. That is the equation of the line. But that is not describing the line segment. The line segment starts at the point 3, negative 4, ends at the point 5, 2. So we have to restrict the domain to be between those values. So all that you do to fix that, I'm going to show you two different ways. You can say that our domain have to be the x's from 3 to 5. That's one way to say it. Or you can say that our x's have to be between 3 and 5. We need to include 3 and 5 so our endpoints are included. So you can write it anything like that. But it takes lines and it just bumps up a little bit of how we kind of would just draw that line segment. And if you were to go into Desmos and you were to put in the line y equals 3x minus 13, and then put in brackets that x is between 3 and 5, it would just give you that line segment, okay? We do have to remember how to do piecewise functions. So let me remind you how to do that. Let's count every other. Yeah, I think we'll have enough room. Let's do every other as 1. So if you want to mark your graph paper accordingly. Okay. So what I would suggest doing anytime we go to graph a piecewise function is notice what your border is. We have a value of 2 where it switches from one equation to the other. So no matter what, over at an x value of 2, just put a little dashed line. That is your border between equations. So you always want to put that border in first. Now our top equation, when x is less than or equal to 2, we're going to use the equation y equals -1/2 x plus 3. Now you'll notice that I rearranged it to put it into slope-intercept form. For me, then I can more quickly visualize the slope and the y-intercept. Now you don't have to, but again, just making it so we are less likely to make a mistake. This equation lives over here. So the y-intercept and the slope is a really good way to graph that line because it's going to go through the y-axis at +3. And then it's going to go down 1/2. But when it hits this line, it is allowed to be equal to it. But I only want the portion that goes this way. Okay. Okay. So that's that one. Now, the other equation, when x is greater than 2, we're going to use the equation y equals 2x minus 5. Now, normally, and you still can, you can start at -5, go up 2 and over 1, up 2 and over 1, but that's going to give you a lot of points on the wrong side. Remember, this line lives over here. So normally in a calculus class or even a pre-calc class, I would say, why aren't you using slope y-intercept to graph the line? But in this case, if we plug in something on the border and something where it lives, then we get its portion of the graph very easily. The border is 2. Now I know it's going to be an open circle, but I still need to know its starting value. If I plug in 2 to that equation, I get -1. If I plug in 3 to that equation, I get +1. So let's label those points. At 2, 1, I would have an open circle. Oh, no, sorry. At 2, 1, I would have an open circle. At, oh, no, I'm sorry. 2, -1, I have an open circle. Goodness. At 3, 1, I have a regular circle, and my graph continues to the right. So hopefully you remember a little bit about how we graph piecewise functions. Now, if you were to start at -5, go up 2 over 1, up 2 over 1, up 2 over 1, and only fill in that portion of the graph and then erase this portion, you can do that. Yeah, that's perfectly acceptable, okay? Everybody good with example 5? Okay. Some things about symmetry that I want to talk about. Last year we talked about symmetry. Please remember that an even function has y-axis symmetry. This is an example of an even function. We could fold it across the y-axis and it folds to a perfect match on both sides. An odd function has origin symmetry. This is an example of an odd function. If we put a little push pin at the origin and spun it 180 degrees, it would appear as if we have not changed it. Now, as far as the mathematics, the algebra of it, so this is the graphical interpretation of what we should see in an even and an odd. But for an even and odd function algebraically, just remember that if you stick in negative x into an even function, it will go away because f of x and f of negative x are the same point. It's because of that symmetry. In an odd function, a point that starts out in this quadrant, f of x, if you make it a negative, it would be the same value as f of negative x. So those are the things you want to remember algebraically, okay? Everybody have that written down? Okay, so let's do some examples. There's a lot of stuff they've shoved into this first lesson. What time's our bell ring? Pretty soon? Okay, so let's finish these three and then we'll continue this tomorrow and then we'll work on some homework. Okay, so 6a, it says, are the following functions odd or even and what's the symmetry? So the first thing you're going to always do is plug in negative x and see what happens. If it disappears, it's even. You know, if it goes right back to the way it looked from the start, it's even. If it is the opposite of what we started with, it's odd. Okay, so if I plug in negative x, because I have an even power surrounding the negative x in both the top and the bottom, it goes right back to where it started. So it is even and has y-axis symmetry. If the negatives all went away and it started, or it went right back to the way it started, it's even and has y-axis symmetry. The second one, if I plug in negative x. So I have to put a negative on each of the x spots. The outer one goes away, but I'm sorry, the outer one stays. The inner one will go away because the absolute value of x and the absolute value of negative x are the same. So isn't that the opposite of what I started with? So this is odd, and it has origin symmetry. And if you were to put that function into Desmos, it should look like, you know, something related to a pinwheel. You could put a push pin in the center, flip it 180 degrees, and not change it. And then the final one here, if I plug in negative x, some of the pieces are going to change. See how the x cubed changed, and so did the x to the fifth, but the 1 did not. So since not all of the pieces were multiplied by negative 1, this is neither of those things. So if you were to look at the graph, it doesn't have y-axis symmetry. It doesn't have origin symmetry, okay? Now, one piece of little homework you got tonight is there is a book and a solution manual in Google Classroom. You need to put it into Notability. They are huge files. So, you know, try while you're here at school, and if you're, you know, doing an activity in a class and you're not using an iPad, put it into Notability. You know, when you have time that your iPad is just kind of idle because it's such large files. So your job is to get your book tonight. We'll finish this tomorrow, and then we'll talk about the homework tomorrow as well. Okay.